Hello. Today we'll be presenting about ERAN, and my name is Gabriel Clark.
I'm Garrett Parker.
My name is Viet Ninh.
Today we're going to be going over ERAN. We're going to start with a high-level introduction, go to a high-level overview, technical background, demo, evaluation, related work, and wrap it up with a conclusion.
So, to do a brief overview of why this problem is important, there are a couple of challenges with AI models today. So, AI models today are often seen as black boxes, with the complex internal workings not fully understood even by the experts. And this can make it difficult to predict how these models will behave in unusual and unforeseen situations. And second, the data we use to train these models influences their robustness. So, for instance, if a model is trained on a limited or biased data set, it may perform poorly when exposed to a more diverse real-world data set. And an example of this is facial recognition. Real-world facial recognition systems are often less accurate at identifying individuals with certain ethnic backgrounds because there's less data labeled on these individuals. And this can have huge ramifications and may lead to poorly classified examples and unequitable action. So alternative approaches are adversarial training and model regularization, but the limitations of these are pretty big. Often they're super expensive, and there's risks of underfitting associated with them. So ERAN, the tool that we chose to use, has a unique approach to this problem. ERAN stands for ETH Robustness Analyzer, and it avoids both some of the computational costs and the risks of underfitting. So a high-level overview of what ERAN does. The robustness verification side creates deformations in the image, which you can see on the bottom here. The G in the first example is deformed by a non-smooth vector field and looks a little bit pixelated. And the second G is deformed by a smooth vector field, which moves pieces of the G in natural ways, like your hand would move. And the other part of it is formal guarantees. So this means that within a certain level of perturbation, that your image will be classified a certain way. And this can be useful in high-risk applications like flight or other examples like that.
So some of the technical background of ERAN is it is implemented using Python. It requires Python 3.6 and uses external libraries like TensorFlow and Onyx for loading models, NumPy for numerical computations, SciPy for linear algebra and mathematical functions, and NetworkX and Matplotlib for plotting. ERAN uses 5 main algorithms and techniques to verify neural networks. The first technique is that it uses satisfiability modulo theories, or SMT solvers. ERAN implements these verifiers for neural networks that are based on encoding the network mathematically. It then uses the SMT solvers to prove the robustness properties of neural networks, which is to prove the robustness against small perturbations, robustness against geometric transformations like rotations, translations, and scaling, and stability against vector field deformations. The second technique that ERAN uses is its abstract interpretation. The technique is a sophisticated approach that involves specialized abstract domains to over-approximate the behavior of neural networks with the primary goal of over-approximating the set of values that a neural network can take during its approximation. It is important for scaling the verification process, ensuring adaptability to different network architectures, and striking a balance between precision and computational efficiency. The third technique that ERAN uses is mixed linear programming, mixed integer linear programming, or MILP. MILP is a mathematical approach used to solve problems where variables are constrained to be integers. How ERAN uses this technique is in the context of neural network verification. This involves expressing the activations of neural networks using binary variables by using binary variables for activation functions like ReLU. The nonlinear behavior of those functions can be translated into a linear form that is compatible with milk. Once translated, it then uses tools like Gurobi, a powerful mathematical optimization solver, to solve the milk problem. The fourth technique that ERAN uses is the K-ReLU framework. The framework is a method for handling the nonlinear nature of ReLU functions activations in a piecewise linear manner. It approximates the activations by unfolding them into multiple linear constraints, which is done to linearize the nonlinear behavior of those functions. This technique refines the analysis and tightens the bounds on neuron activations, and through this, it improves the accuracy and effectiveness of the neural network verification process. The last technique that it uses is linear programming relaxations. This is a collection of techniques like triangle-based piecewise linear approximations of activations that are used to optimize bounds on neurons. By doing this, ERAN is able to decrease the complexity and approximate different parts of the model. For example, when running this technique on a ReLU function, activation function, it makes the function effectively linear and allows ERAN to perform better approximations on them.
All right, now we're going to do a live demo. Basically, this is running already in a Docker container. So in order to get this to run quite properly, we had to run it in a Docker container. We start Python 3, and it's just going to be running with an epsilon of like 0.05 for a 5-layer 100 neuron model. This is going to be classifying on the MNIST data set. Because it's a relatively small size model, this runs quite quickly, so we're able to run through most all of it right here. We can see as we go through, it's basically classifying whether it runs through the actual model, classifying each image, and then does the perturbations to see if it actually can be verified.
At this time, I'd also like to hit on what the epsilon value is that we just talked about. So ERAN's epsilon value specifies a bound on how much perturbation it does to the input images. So in that first example we showed, where the vectors were distorting the input image, those vectors' sizes are controlled by epsilon. And so if you want a more robust network, you can increase epsilon and you'll verify less examples. If you want a less correct network, or you have a smaller network, you can decrease epsilon and verify fewer examples.
So we can see for this particular model, it went through and correctly identified about 98 of the 100 images, and was actually able to verify only about 79. So that's saying that the other couple of the like 10 or 20 didn't pass the perturbations. So we can't necessarily say that the model will always get those ones correct with that level of perturbation. So for evaluating the model, we decided to analyze it on the CIFAR 10 data set, which is commonly used as a benchmark for a lot of other models. If you've done neural networks, you've probably used it before. The goal overall is to classify images into 1 of 10 categories, like a car, a bird, or like a cat or something. And the goal for the ERAN here is to analyze the model's robustness against these perturbations that we just mentioned, such as slight changes in pixel values due to different lighting conditions that these actual images may be in, camera quality, or even adversarial attacks. In order to classify CIFAR with high accuracy, we chose a kind of larger network. It was a convolutional network that had about 7,000 parameters and about 3 layers in sigmoid activation. Through training, it was able to reach about a 0.0078 epsilon value and took about 3.5 hours to run.
So ERAN is a part of a growing field of tools used for verifying and analyzing neural networks. Some of these other tools in this domain are AI2, ReLUplex, Deep Explore, and Deep Test. So AI2 uses a hybrid approach that combines both static and dynamic analysis to identify software vulnerabilities. This allows AI2 to leverage the precision of static analysis with the practical coverage of dynamic methods to enhance effectiveness in vulnerability detection. ReLUplex is an SMT solver that specializes in verifying properties of neural networks Its contribution lies in its rigorous approach to ensuring the reliability and safety of neural networks. Deep Explorer and Deep Test both employ differential testing techniques that involve generating test inputs. These inputs can expose discrepancies in neural network outputs under different conditions, revealing hidden vulnerabilities and wrong behavior.
In conclusion, ERAN represents a significant leap forward in the quest for reliable and robust AI systems. Its ability to analyze and verify neural networks across a range of architectures and conditions positions it as an indispensable tool in the deployment and validation of AI models. As AI continues to evolve and integrate into more critical aspects of our society, tools like ERAN will play a critical role in ensuring these technologies can be trusted and relied upon.
Thank you for watching.